We're going to cover the basics of root locus, and in this first part we are going to talk about how to set up the drawing for it. We're going to draw this on the S-plane. And before we actually start drawing the root locus itself, we have to understand our pole equation here a little bit more. And we're going to start with just an expression. So the expression for G and H, if we say that G of H, we'll just lump them together. So you multiply them together, you get some expression. That expression will have some numerator as a function of S and some denominator as a function of S. So we want to look at our poles here. And so if we plug this equation into our pole equation, we get 1 plus k times, now we're just substituting this in. So it'll be some numerator expression in terms of S and some denominator expression. And this has to be equal to 0 to evaluate the poles. Now, we usually want to get rid of any s's in the denominator, so we can multiply this whole expression by d of s. And then we can solve it here. So here we have our k times ns equals 0. So we can get it in this form. And remember our denominator here, these would be the zeros, sorry, the poles of the systems. So these would represent the poles, and the numerator represents the zeros of this system here. And what we're going to do is we're going to vary k starting from 0 and into infinity. Look at this equation though. Think for a second, what if k is equal to 0? So if k is equal to 0, our expression simply becomes d of s is equal to 0. Right? So the poles of this system, of our G times H, the poles of that system are the poles of our closed loop system. Okay? Then, if, let's take the other extreme, so if k goes to infinity, so if the k goes to infinity here, these are essentially going to completely be ignored, and then k dominates, and all we have is n of s is going to be equal to 0. Okay, and this is the numerator, so these are the poles, sorry, the zeros. These are the zeros, and these are the poles. The other example we gave, these are the poles of our GH here, and these are the zeros. So in a sense, if k is 0, the poles of this thing are our closed loop poles. Okay? And if k is infinitely high, the zeros of this system become our closed loop poles. So we're going to use those as our starting point. So when k equals 0, we're going to start from this point, from the poles of our GH, and we're going to end, because we're going to take k from 0 all the way to infinity, and we're going to end at the zeros of the system. Okay, so we're going to draw that on our S map. So say we have, I'm just going to make an arbitrary example here. So if we started and we had an x, a pole from our original system here, and we had a 0 here, this would be our starting point and our end point. Also note that we're going to have a bunch of different lines going through here. So this line will look like this. That's one branch is what we call it. So this is a branch. Oops. Branch. And the number of branches for a system is equal to the number of closed loop poles. So if we have, it's the closed loop, right? So it's this full expression. So if we have 1, we'll have 1 branch. If we have 20, we'd have 20 different branches. So we have 20 different lines that are going to map from k value equaling 0 to infinity. Okay, so this is the basics. The important things that you need to remember here are the number of branches that we're going to see are the number of closed loop poles, and we start at the poles, so poles of, and I'll just write it here again, G, S, H, S. That's where we start, and we end at the zeros of our G, S, H, S equation. Okay? Now let's take an example. So let's do a very simple example of, this is the equation for G and times H here. Just S minus 1 divided by S plus 3. So first thing we need to do, remember, we need to find our starting point and our end point. So to do that, we look for the poles and zeros of our G times H expression. So here it is. Our 0, we can see easily, is 1, positive 1. And our pole is at negative 3. Okay? And note this would be a stable function on its own. So that's good to know. And so what we'll do first is, here's our S-plane, and we will simply draw those 2 points on the plane. So we'll start with our 0 at 1, and call us 1, have our 0 here. And then at negative 3, so 1, 2, 3, so I'll put it up here. Negative 3, we put our pole. And let's check the number of branches. Well, in this system, we're going to have just one pole. And if you're not quite convinced of that, let's actually multiply it out. So if we did this multiplication out, and I'm going to skip one step, so we know that this denominator would be multiplied and end up over here. So we're going to do that. S plus 3, right, the pole, the denominator of this expression, plus k times the numerator, S minus 1, is equal to 0. And so here the highest order is S, here the highest order of S, and so our number of poles in the closed loop system is simply 1. Okay, and note, most of the time we are dealing with proper functions, so usually it will be the same magnitude as the denominator here, but if you're not sure, you can always go through this and check. Okay, so here we have just one pole, so we will have number of branches, one closed loop pole, so we'll have one branch. Okay, so we've followed these rules, looks great. So we've drawn this on our S-plane. Now the next question is, what path does this take? We know we start here, and we end here. But which path do we go on? Do we go straight across? Do we go up and over? Do we go down? Do we go all around the map and eventually end up there? That's a good question. That's the slightly harder one to explain. I'll tell you the answer. What we're going to do is end up just going straight across the real axis here. And so that will actually end up being your root locus path. And usually you draw some little arrow just to indicate, but we draw the X for the start, meaning the pole of this system, and the 0, so you know which way it's going based on the X and the 0 position. But I'm going to try to explain this. It's a little bit hard, but the other thing that we need to remember is, we derived this last time, the angle of this expression, so G of S, H of S, has to be equal to 180 degrees. So the path that we have to take is constrained to this. It has to meet this constraint, essentially. So our path here, our real value, so if we pick any real value here in between these two, between negative 3 and 1, if we put that into our equation, we'll actually see that we'll get a 180 value out. So let's just take a test point first to just try to understand it. Let's take this negative 1 as our value. So let's let S equal negative 1, and we're going to throw that into our equation here. And we'll get negative 1 minus 1 over negative 1 plus 3. So we'll get a negative 2 over positive 2, which is negative 1. That looks good. This is actually the magnitude that we need. So we need negative 1, and we see the angle is going in the negative direction, right? So it's 180. So this satisfies this constraint. And actually, if you test every single real point on here, they will also satisfy that constraint between those two values. So then you know that this constraint is satisfied, and that is the path it will take. Another thing that we can look at, and this is a little bit confusing to explain, I'll give it my best go here. We can look at these 2 points. So I'll try to draw it here. So if we want to test a point, what we can do is take a point, and if we look at what this means, so say this is S, say this is, I'm just going to arbitrarily say it's -1 minus or plus 2j, so just some point, and we want to test it, we can plug it into this equation, into here, and it'll spit out our value, and we can figure out the angle and the magnitude of it. And here we're looking for the magnitude, or sorry, the angle, right? It has to follow this constraint, and you can see if it meets this or not. Another way to visualize it is if you kind of go back to your vector math, this s minus 1 is actually the same as if you put this point in here. It's the vector from this point, this pole, oh, sorry, that's the s minus 1, it's actually be this one, this pole to that point. And since s is the same, we'll also look at this vector. So it's the vector from the pole to the point that you're trying to test. And that vector, one has a magnitude and also has a pole. Sorry, magnitude and an angle. Okay, so this has an angle here, some value, and this also has an angle here, some other value. And when if we wanted to divide 2 values, so say we have, I'm not going to give the actual value, just alpha and some angle, theta 1, and we have a beta and some angle, theta 2. If we want to evaluate these, we would get alpha over beta, and we actually end up subtracting the angles, so theta 1 minus theta 2. So if we look at this value, so if we had this value, and we subtract this value, in order for the angles to work out, it has to be exactly 180. If you go through the math of this, you'll find that it will not be 180 for any of these values outside. So it is only true for the values on the real axis. So if we just do this math one more time for this test point here. So if we look at the distance here, so the vector from -3 to this -1, it is value 2, magnitude, right? So 2 units. And the angle is 0, because it's pointing in this direction, to this point. Okay? Let's look at the other one. So the magnitude from now this to this point, so it goes this way, it is also 2, but its angle is -180, or 180, it doesn't really matter, they're the same. So we'll say it's positive. So if we evaluate this further, we'll get 1, we subtract these 2 angles, -180 degrees. -180 is the same as +180, and so this satisfies this constraint. And if you go through, you'll see that that is true for every single point on here, but if you just move up just a little bit, it will no longer be true. So that is, if you followed my explanation, how you can show that this path between these two has to be on the real axis. Okay, so I'm going to stop here, but this, so the line that we drew here, so this blue line, starting at -3, which is the pole of our g times h, straight line to the 0, which was at +1. This in itself is the root locus, and it would go from the left to the right here, from our starting point to our end point.